Hi guys, today we're going to talk about the sinusoidal nature of simple harmonic motion. That's what we're going to start discussing today in this video. And then towards the end of the video we're going to review a little bit of things about waves, primarily the difference between transverse, longitudinal, some vocab words, kind of how waves behave in certain situations. So most of the second part should be a review. This stuff at the beginning might be a little bit new to y'all. So before we start talking about this sinusoidal nature and what that means, is we're going to first discuss the differences between a mass and spring system and a pendulum. And hopefully you guys saw this difference in your lab the other day. But whenever you are trying to find the period of a pendulum, or I'm sorry, period of a mass and spring, or how long it takes one complete oscillation to happen, we can use this expression down here. And this expression says 2 pi times the square root of the mass divided by the spring constant. And hopefully your graphs will show this relationship when you do them in lab. If not, it's okay, but this is what we're aiming for. So, since frequency is equal to 1 over the period, then to find the frequency of a mass and spring combo, you would just take the inverse of that previous equation. So the frequency would be 1 over 2 pi times the square root of k over n. Now a pendulum is a little bit different. Remember we talked about how pendulums can show simple harmonic motion, and we don't necessarily make the displacement be very large in these situations. Pendulums tend to work best when the displacement is very, very small, so when you don't really pull the bob back past 20 or 30 degrees. So here's a little picture of a pendulum in action for you, and essentially it's the same thing as a mass and spring combo, where you have positions of maximum displacement, you have positions of maximum potential energy, and then as it swings through the center you get moments of maximum velocity, maximum kinetic energy, and no potential. So with regards to the period of a pendulum, this is something you guys should have seen last year in pre-AP. We can find the period by doing 2 pi times the square root of L over g, where L is the length of the pendulum and g is the acceleration due to gravity. Hopefully what you guys saw in both of these cases, for a pendulum and a mass and spring combo, the displacement doesn't matter. For a pendulum, how far you are pulling the pendulum to the side doesn't affect the period at all. The only thing that will is the length of the string and the gravity. Okay, so let's go into this sinusoidal nature of simple harmonic motion. You can, when you create graphs of simple harmonic motion, we're going to focus on the mass and spring combo right now. If you were to graph these position versus time, velocity versus time, and acceleration versus time, what you're going to end up looking at are 3 different sinusoidal functions. And hopefully you guys have seen these in pre-cal or calculus, depending on what you're in. So let's do the displacement versus time first and talk about what that graph means in an equation for this line. So displacement versus time, here, this is your displacement, and here is your timeline. Okay, we're going to look at this motion for one period, or one full oscillation of the mass and spring combo. So down here at the end of my line, this will represent the period, or the time for one complete oscillation. At the start, I'm going to start at maximum amplitude here. I'm pulling the spring all the way back, and I'm going to let it release. Here in the middle of the line we have a position which represents halfway through the cycle. Let's do one for 1/4 of the way through the cycle, and let's do one for 3/4 of the way through the cycle here. So we're going to describe what's happening with the spring as it goes through a cycle of motion. If it starts at maximum amplitude, it's going to end at maximum amplitude here. Remember, a cycle is one complete vibration, or how long it takes to come back to where it started. So if it starts here, it'll end there at the end of the cycle. Halfway through the cycle, let's think about what's happened. Here's your spring, here's your block out here. Once it's maximally compressed here, that's when it's gone through half of its cycle. So that will be down here at a negative amplitude. So where does it experience moments of 0 amplitude? Well, when it's going through equilibrium. And where will it be going through equilibrium? Well, it happens to be here at a fourth of the way through the cycle and here at 3/4 of the way through the cycle. So when you connect these lines, and hopefully you guys are doing this better than me, it should be curvy, not so sharp, you're going to end up with a cosine graph. So to find the displacement of a mass and spring system at any moment along its oscillation, we can use this expression where x is equal to the maximum amplitude times cosine times 2 pi frequency times time. Now they go through in your textbook where this comes from. If you guys are interested in reading it, you can. I don't have time in the video, so I'm not going to do it now, but another way to say it is A times cosine. If we wanted to use the period and not frequency, remember frequency is 1 over period. So we can do 2 pi times t over period. So if we use this expression, if we know the time that we're trying to find the location of our oscillator at, and we know the period of oscillation, we can figure out at any moment along its cycle where that object would be located. Now we can do another graph like this for velocity time. And when you do velocity time, you're going to end up with a sine graph. So here's this, and here's your full cycle. Here's half of a cycle. Now, when you are talking velocity, you have a Vmax here, and you also have a negative Vmax here. At the start of an oscillation, when the spring is completely pulled outwards, the velocity of that spring is 0. It reaches moments of maximum velocity when it goes through the equilibrium point. And those equilibrium points happen, as we saw in our last graph, at the quarter marks, fourth of a period, and then up here we've got another fourth of a period. So for velocity, what we're looking at in this case, I curved that kind of poorly. This is a sine graph, and this is a negative sine graph. So to find the speed of an oscillator at any moment along its path, we can say negative Vmax, we'll just call it, sine, and then the same expression as before. Or if you want to use the period, we have Vmax sine 2 pi t over capital T. All right, let's go ahead and go back to the PowerPoint. All right, so let's look at this example, and we'll do this one together. So for this one, an air track glider oscillates horizontally on a spring, frequency of 0.5 hertz. Glider is pulled to the right, 12 centimeters released. Glider B after 1 second after its release, and what is its velocity at this point? Well, for this one, our frequency is 0.5 hertz. So that means that our period in this case is 2 seconds. The glider is pulled back to a position of 0.12 centimeters here. So we can draw a graph if we'd like to. This one's going to be pretty easy because the numbers are nice and clean and simple. But if I didn't want to know something exactly halfway between this period, drawing a graph might help. If it doesn't help your brain, then don't do it. But it definitely helps mine sometimes. So our equation is x equals maximum amplitude times cosine 2 pi. Now because I know the frequency and I know the period, I can use either expression. I'm just going to use the frequency expression because it's a little bit easier for me to write. So the maximum amplitude in this case is going to be your 0.12 centimeters. Now when we do this part here, this is going to be 0. Let's see if I can freestyle this. Okay. This is what our graph ends up looking like. We know that 1 second is halfway through the cycle, so at that moment, halfway through, we should be experiencing maximum amplitude, but in the opposite direction. And when I plug this into the calculator, I definitely get negative 0.12 meters. Now remember that for these problems, your calculator needs to be in radians. Now, because we're at a period of maximum amplitude here, that means our velocity at this point is going to be 0. And again, if you didn't know that, you could plug that into our other expression and figure that part out. But because it's at maximum amplitude, the velocity is going to be 0. Okay, I want you guys to try to do this one. I'll pause it for you. You guys can pause the video and try to do this one on your own. And I will write the answers on the paper on the next page because we're running out of time. So for this one, your acceleration, for part A, your frequency is 0.4 hertz. If you found the period is 2.5 seconds, or there you go. For part B, they wanted to know when the max speed was, when is it, and what is it. The max speed happens at 0.63 seconds, and for the max speed, is 0.25 meters per second. For the max speed, I'm not sure if I mentioned this in the previous slide, but the max speed, if you don't know it, you can use this expression, 2 pi times the frequency times time, to figure out what your maximum speed would be. And then the third part of the problem asks what are the position and velocity 4 seconds after you release the toy. So for part C, your answer for position should be 0.081 meters, or 8.1 centimeters. And then your velocity should be 0.15 meters per second. All right. So let's talk real quick about some recapping some waves vocabulary. Resonance. Remember that resonance happens when something is vibrating and it causes something else to vibrate at its natural frequency. We encounter this actually quite a lot. If you guys are in band, you've probably experienced this if you're in a room with a bunch of instruments. And somebody plays a note and you can feel your instrument starting to vibrate. That's an example of resonance. Being able to shatter a wine glass with your voice like some opera singers can do. That's an example of resonance. Last year I showed my students the video of the Tacoma Narrows Bridge, the bridge that looked like a big wave because the wind that was blowing through the canyon there was blowing at the bridge's natural frequency, and so it caused it to start vibrating. There's all kinds of examples of resonance. I have a couple of examples I can show y'all in class when we return. But if you haven't seen any of these, I suggest looking at them up on YouTube because they're pretty cool examples. Okay, waves only transfer energy. They do not transfer matter. If you guys remember that from pre-AP before. So I have a little demo here that I want to show y'all. And this, if you focus just solely on the, I'll do no end. If you focus solely on the green dots, what you're going to see is the fact that the green dots don't actually move anywhere. They're not going down the string. They're only vibrating up and down like this. So that tells us that waves are not actually pushing matter along. I'm not actually pushing the string out the window. All I'm doing is transferring energy from one molecule of the string to the other. So let's see if we can't make it a little slower so we can see what's happening. If you focus just on this green dot right here, you can see it's just moving up and down, and it's not moving down the length of the string. All right, speed of a wave. This is our equation we used last year, and we're still going to use it this year. Velocity equals frequency times wavelength, and the answer is, of course, in meters per second. We can also use a different equation. It depends on the medium that the wave is traveling through. For a wave through a string, this is typically what we look at for this equation, but the tension of the string becomes important as well as the mass per unit length. This this makes sense because if the tension is higher here in the string, then that means that the speed will be higher. And if the mass per unit length is larger, then that means that the string will have more inertia, so it'll be more difficult to get it to move, so your velocity will be smaller. Transverse versus longitudinal. Transverse waves, remember, are waves that vibrate perpendicular to the direction of travel. So these are things like water waves are good examples of transverse waves. These are our typical waves that vibrate up and down, but they move left to right. Longitudinal waves vibrate parallel to the direction of travel. So these are examples of longitudinal waves would be like sound waves are longitudinal waves. Light waves are transverse waves. Remember that transverse waves have regions, crests, which are the high regions, troughs, which are the low regions. Wavelengths are the lengths from crest to crest or node to node, if you guys remember that from last year. That's a wavelength. The amplitude of a wave is the height from equilibrium to the position on the wave. Longitudinal waves have crests and troughs as well, but they're called compressions. And this book calls them extensions, which I like better than the other word that was used in y'all's pre-AP book. But for compressions, as the wave moves along, you're going to have regions of higher density there and regions where they're kind of spread out. So your compressions are going to be the higher density regions and your extensions are going to be the spread out regions. Same things as a crest and a trough, just in a linear sense instead of up and down. All right, intensity, this is the last thing we're going to discuss. Intensity is equal to power divided by area. Most of the times we talk about intensity with sound waves, and so because of that, sound waves are spherical, so the area is 4 pi r squared. Power divided by that. For intensity, we measure intensity of waves in watts per meter squared, although sometimes you will hear it talked about in decibels. Your book doesn't have a decibel chart conversion, I don't think, not one that I saw earlier, but this is the unit for intensity here. I'm going to go ahead and stop there. You guys will get some practice with this stuff on Friday, and if y'all have any questions, you can email me.